So, what we have to do is, I think we are on to lecture number 4. It's not 3, it's lecture number 4. And in the previous lecture, we had finished interference and we had finished Young's double slit experiment. What we are going to do in this particular chapter, in this particular class, we are going to start with the next concept, which is known as diffraction. We have already heard the term diffraction in YDSE. Do we remember it, beta?
Yes, sir.
We had seen that in YDSE, when we are trying to create the two sources, the two coherent sources, we were using the phenomena of diffraction, and by diffraction, we were converting a single source into two coherent sources. That was diffraction. Now is the time that we understand what is the meaning of the term diffraction, and for that we will I will take you to your next screen. And here it comes, diffraction. Do you have any idea about the term diffraction?
Yes, sir.
What do you think is diffraction? Tell me. Yes? I can't hear you. What is the meaning of the term diffraction? Tell me. It's on your screen right now. What is the meaning of the term diffraction? It is the spreading, or instead of using the word spreading, we can use the term bending. Instead of spreading, we can use the term bending. Bending of light rays. If you know that light always travels in a straight line, yes or no? Light waves, they always travel in a straight line, but when it encounters an obstacle, and remember, this obstacle that we are talking about should be very small. The obstacle that we are talking about should be very small. They must be of the order of the wavelength of the wave. Any wave, whether it's light or any radiation, if normally it will always move in a straight line, but if it encounters any sort of an obstacle which is of the same order as the wavelength, if the wavelength is in Armstrong unit, the obstacle should also be in Armstrong units. If such an obstacle happens, if such an obstacle appears in its path, what will the light wave or any wave do? It will start to bend or spread. This phenomena of bending or spreading of light waves, or any wave for that matter, here we are dealing with light waves. Any wave, when it encounters an obstacle, the phenomena of bending of light waves around the sharp edges of an opaque object or aperture or an obstacle is known as diffraction. And you must remember the size of the obstacle. If A is the size of the obstacle, A by lambda, where lambda is the wavelength of the wave that we are talking about, A by lambda should be approximately equal to 1. Then only the phenomena of diffraction happens. Remember, there was a question that we did in interference where we were gradually increasing the width of the slit, and we saw that the phenomena of interference will disappear. Why will it disappear? Because the phenomena of diffraction will disappear, and we shall not have two coherent sources. Do we understand this?
Yes, sir.
Okay, I'll give you a minute to note this down. Do you have this sheet with you? You have this sheet with you, beta?
Yes, sir.
Okay, please note it down. What is the meaning of term diffraction? This is a very small topic, diffraction and polarization. And if possible, we will try to wind it up in today's class. Diffraction, bending of light waves. Have you noted it down, beta?
1 minute, sir.
Okay.
Completed, sir. Sir, completed. Hello.
Understand that where we can observe diffraction. We have seen that the size of the obstacle should be equal to the wavelength of the light, and here are we are going to discuss this in detail because any of these conditions can come as question in your exam. So the first thing that you must remember, and it's a very important note, greater the wavelength, higher will be the degree of diffraction. If the wavelength is more, you can observe high degree of diffraction. Remember, sound waves and radio waves, they have much larger wavelength compared to light. Wavelength of sound or wavelength of radio waves is much larger compared to light, and therefore it is easier to see diffraction in sound waves and radio waves because their wavelength is much larger. To get diffraction from light waves, we must create an obstacle, we must create an opening which is very small. Remember, light wavelength is very small, and therefore to observe diffraction for light waves, we have to create very small openings. Remember, if the size of the obstacle is very small compared to wavelength, diffraction is not possible. If it is very large, also diffraction is not possible. The only condition where diffraction is possible is when the size of the obstacle is nearly equal to the wavelength of the wave that we are talking about. This is a very important result because I have seen question on this come in the exam. If the wavelength is very large, what are the conditions possible? So you can really mark, you can easily mark that diffraction is definitely not possible. Now, the next step, and I'll give you time to write it once I'm done with this screen, is we had observed because of interference, maxima and minima happen. All the maximas for young double slit experiment, they are of equal width and equal intensities. We had done a question based on that. Now, as a result of diffraction also, you will find maximas and minimas, but here the maxima and minima are of unequal, and remember this term, they are of unequal intensity. So if sometimes they ask in a question the difference between interference and diffraction, we can always say that in interference, maxima and minima were of the same width and they have equal intensities, whereas in diffraction, they are having unequal intensities. Why is that so? Remember, interference, we only had two sources, but in diffraction, we have superposition by infinite number of coherent sources of the same wavefront. Remember, in diffraction, there are not two coherent sources. There are infinite number of sources which are created from a single source on the same wavefront. And therefore, we will have maximas and minimas, but they will be of unequal intensities. Please mark this, a very important point. Most of the questions that you will find in diffraction, polarization, interference, they will be of theoretical nature. You can simply mark them if you know it. And these are the points that you need to remember. I'll give you a minute to note this point down. Have you noted it down, beta?
Yes, sir.
Okay. Then this is what you can see as diffraction. This is a diagram of diffraction. You see that there is a wave coming from here. This is a slit or a small opening. Do you see this small opening, slit or small opening? Yes or no? On the screen.
Yes, sir.
Now, if the width of this slit is A and the wavelength of this wave is lambda, you must remember that A by lambda should be approximately equal to 1. Do we remember this? What we will see here is the shadow that we will see will be bigger than the object. That means these light waves have bended slightly. Do you see this bending here? Yes or no?
Yes, sir.
This is the phenomena of diffraction. Similarly, here there was an opening. Here there is an obstacle. We have put a small disk in front of a light source. Do we see this? This diagram is not there in your notes. That is why I have shown it from a different sheet. Here I have put an obstacle. Now when you see the size of the obstacle is very small, but the size of the shadow is large. This is because the light has bended. Do we understand this? This is the phenomena of diffraction. Shall I move ahead?
Yes, sir.
Now, whenever we see the phenomena of diffraction, there will be two types of diffraction that we have to encounter. Again, these are known as Fresnel diffraction number 1 and Fraunhofer diffraction number 2. Again, Fresnel diffraction is not there in your notes because that is not a part of your curriculum, but you can easily ask what is Fresnel diffraction and what is Fraunhofer diffraction. Do you see the difference between Fresnel diffraction and Fraunhofer diffraction? If I talk about point number 1, the source or the screen or both are at finite distance from the diffracting device. This is the diffracting device which is creating the diffraction. This type of diffraction is known as Fresnel diffraction. This is a common example. I have a source here. In front of this source, I put an obstacle or I put a small slit. The diffraction pattern is seen on this screen. This type of diffraction is known as Fresnel diffraction, where object and the screen are at finite distance from each other. In the second case, in case of Fraunhofer diffraction, what do you see? The light source, it is at a very large distance. It is infinite. It's coming from a very large distance. That means the distance between the source and the screen is infinite. The diffraction that I see in this case is known as Fraunhofer diffraction. To divert the rays on the screen, I use a convex lens. So basically in Fraunhofer diffraction, I use a lens. The object is at, the source is at infinity and I use a lens. And in Fresnel diffraction, I have source and screen both at finite distances from each other. Do we understand the difference here?
Yes, sir.
Please, you will have to note this down because it is not there in your sheet. So note these two diagrams down. You may not note the examples if you don't want, but you will have to note down the two cases with the two diagrams, and I'll give you 2 minutes to do that. Have you noted it down, beta?
Yes, sir.
Okay. That takes us to this we'll have to understand Fraunhofer diffraction, and we'll have to note down some formulae for this Fraunhofer diffraction. As you can see, we have a slit here whose width is A. Do you see this? We have a slit whose width is A. Remember this A by lambda is approximately equal to 1. So this slit must be of the same size, same order as that of the wavelength. As you can see, there are a large number of waves which are going, and this large number of waves which are going, infinite number of wave of the same wavefront, they are superimposing each other at this point P. Do we see this? This is somewhat similar to the superposition that we saw in interference. The only difference is in interference, we only had two waves. Here we have an infinitely large number of waves. Do we understand this? This
Yes,
is
sir.
the central point O, and the point P is where we are seeing the wave superimposing. The waves are going to superimpose on this screen, and we are going to get a diffraction pattern on this screen. Remember, in interference, we had two slits. In diffraction, we only have one slit. In interference, we had we had two waves superimposing each other. In diffraction, we have infinite number of waves superimposing each other. We will also see more differences. The table is already there. I'll explain it to you. But once we must understand what is Fraunhofer diffraction, you will have to draw this diagram, and based on this diagram, we will see what is happening here. I'll give you 2 minutes to draw this diagram. Please draw it, beta. Diffraction is very simple. We just have to go through two formulas and we are done. And I'm expecting a question from this side.
Completed, sir.
Okay, bacha, you have drawn that diagram. In that diagram, we had used lens to focus the rays on the screen. Now, normal diagram that you see for diffraction by a single slit will look like this. Do you see this diagram? And from this diagram, we can understand what is happening here. This diagram looks similar to what we had done in interference. In interference, we had two slits, S1 and S2, and D was the distance between, small d was the distance between the two slits. Here what we see, bacha, is instead of two slits, we only have one slit, and D is the width of that slit. Do we understand the difference? Yes or no?
Yes, sir.
In interference, we had two slits. The distance between the two slits was given by small d. Here, instead of two slits, we only have one slit, and d tells us the width of the slits. Width of the slits. Do we understand this? Yes or no?
Yes, sir.
Okay. What else? In Young's double slit experiment, we also had capital D. Capital D was the distance between the slit and the screen. Here also we have the same thing. Capital D is the distance between the slit and the screen. Do we understand this?
Yes, sir.
Similar to the interference, we had this small distance as the path difference between the two waves, and this was d sine theta. So everything looks similar here. The only thing that looks different here is how the fringes are formed. You can see this one, the biggest one, is the central bright fringe. Do we see this?
Yes, sir.
Central bright fringe is having the maximum intensity. Central bright fringe is having the maximum intensity, and the distance from here to here is known as the width of the central dark fringe. Do we understand this?
Sir.
Okay. This is known as the width of the central dark fringe. Will you remember this? And as we go progressively on the other maximas, the intensity is going down. Do you see this intensity going down?
Yes, sir.
That is what you need to draw. If you can draw this diagram and draw this diagram, you can tackle any question that comes on this particular topic of diffraction. Can you do that for me? I'll give you 2 minutes. Can you do that? I'll give you 2 minutes to draw this diagram. Remember, this diagram is not given in your sheet. Your sheet, similar diagram is given. We will go through that diagram as well. But please note down this diagram from here. Have you drawn the diagram, beta?
Yes, sir.
Okay, then you'll have to note down these points from this sheet. Similar points are given in your sheet as well, but you will note down the points from this sheet. The first point and the most important one is the width of the central maxima. The total width of the central maxima is 2 times lambda capital D by D. And if I talk about the angular width, and I will show it with the diagram in your sheet, what is the angular width? The angular width is given by 2 times lambda by D. Remember, these formulas are different from the formula that we had read in interference. In interference, the fringe width was lambda D by D. Here it is 2 times lambda D by D for central maxima. For other maximas, it is lambda D by D. We will see all these points in your notes. Don't worry. Now, again, remember, minima occurs, and a very important point here, minima occurs where the path difference is n lambda. In the previous case, we had maxima occurring when the path difference was n lambda. Do we remember this?
Yes, sir.
Here we have minima occurring when the path difference is n lambda. That is, path difference is d sine theta. D sine theta is n lambda, or sine theta is n lambda by d. To get the position of the first minima, put n as 1. To get the position of second maxima, put n as 2, and so on. Minima occurs when the path difference is n lambda. So what about maxima? Point number 3. The secondary maxima occurs. The secondary maxima occurs when the path difference is 2n plus 1 lambda by 2, or you can write 2n minus 1 lambda by 2. The only difference it will make is from where the n starts. If you write 2n plus 1, the n will start from 1. That means to get the value of first secondary maxima, you will have to write n as 1, and that is how you can find out the position of the secondary maximas. The path difference is 2n plus 1 lambda by 2, or the value of sine theta for maxima. Remember, this is for maxima and this is for minima. Can you remember this? It is reverse of your interference. In the next slide, we'll also go through the difference between interference and diffraction to make all these points very, very clear. Can you note down all these points, bacha?
Sir.
I will give you 3 minutes to note down this point. Then we will go through your sheet and try to make more sense of these points. And I will show you what is the angular weight it is given in the sheet. I'll give you 2 minutes to note it down. Have you noted it down, beta?
Yes, sir.
Okay. That takes me to the sheet wala diagram that you have. Remember, this is your central maxima. Do you see the central maxima? Yes or no? And this is the width of the central maxima. This is the angular width of the central maxima, which is given by the formula of 2 lambda by A. Do we see this, beta? This is the angular width of the central maxima. Here we have first minima on this side, first minima on this side. Here we have second minima on this side, and this is second minima on this side. Do we see this? Yes or no?
Yes, sir.
Do we see this? Yes or no?
Yes, sir.
If I talk about the value of the uh, fringe width, the formula that we had seen was 2 times d lambda by small d. Here in your sheet, the formula is given in a different way. Here we have assumed that we are using a convex lens, and therefore in place of d we have used f. In place of capital D we have used f. Remember, this a and d are same. A is the width of the slit. Instead of calling it as A, we can also call it as small d. Do we understand the difference between the two formulas that we are seeing? So, if the distance between the slit and the screen is given, you can use this formula. If the focal length of the lens is given, you can use this formula. Is it clear to everyone? If the distance of the slit and the screen is given, you use the formula d 2 times d lambda by small d. If the focal length of the lens is given, you use the formula 2 times f lambda by d. Do we understand this?
Yes, sir.
You'll have to draw this diagram to understand the meaning of the angular fringe width. This is the diagram from your sheet. If you don't want to draw it, you can mark it on the sheet, and then we can move ahead. I'll give you 2 minutes to do this. Have you drawn this, beta?
Yes, sir.
Okay. Then you move on to the next slide, and these are important points to remember. Remember, each and every of these important points is a potential question in itself. The first point is an information-based point. Who discovered diffraction? It is Grimaldi who discovered diffraction. Second point is intensity of diffraction pattern decreases. Remember this, intensity of diffraction pattern decreases if the size of the obstacle is increased. So a very important point, intensity of diffraction pattern decreases if the size of the obstacle is increased. Okay, I think I've lost connection here. Just a minute. Well, can you see me? Can you see me, bacha? Am I audible and visible to you, beta? Can you see me, beta? So what we were discussing were the important points to remember in diffraction. Remember the third point. In both diffraction and interference, we have superposition of waves. When we have say two coherent sources, we have interference. When we have waves from the same wavefront, the superposition when it happens is known as diffraction. So basically, in interference, we have two coherent sources and two different wavefronts. In diffraction, we have one wavefront and we have infinite coherent sources from that wavefront. That is how we create diffraction. Is it clear to everyone?
Sir.
Yes or no?
Yes, sir.
Okay, light has come. That is great. So that is the difference between interference and diffraction. We will see them in a tabular form as well, because these are the important points and I want you to remember these important points. Point number 4, interference fringes have equal weight but diffraction fringes have unequal weight. Do we understand this? In diffraction pattern, intensity of bright fringes is different, but interference, it is equal. So even the intensities and fringe widths both are not equal. For the central bright fringe, we have more intensity in diffraction, but in interference, whether it is central bright fringe or other bright fringes, we have equal intensities. Do we understand this? For dark fringes, in interference, the intensity is 0, but in diffraction, it is not equal to 0. Diffraction is only observed in the geometrical shadow, in the shadow wala region. Central bright fringe, and this is a very important point, central bright fringe has double width in comparison to the other. So these are the important points. Basically, these important points are telling us the difference between interference and diffraction, and if you can understand these, it will be very nice. Do we understand this? Do we understand these differences? Yes or no? No or yes?
Yes, sir.
I will give you a minute to note these things down. We will also see them in a tabular form. In a tabular form, it would be easier for you to understand this. I'll give you a minute. Note it down. Okay then. Here again in a tabular form, we have differences between interference and diffraction. Very important point because most of the questions are going to come from here. In interference, we have, two coherent sources and two wavefronts. We have interference, or we have superposition of two coherent sources and two wavefronts. Here we have one coherent sources, one wavefront, and with one coherent source and one wavefront, we are having infinite superpositions. Do we understand this?
Yes, sir.
All fringes, whether they are bright or dark, whether it is central or secondary, all are having same width. Here fringes are having unequal width. Central maxima is having 2 times the width. We will also see this formula. Width of fringes, bright fringes is equal to other fringes. Width of bright fringes is double of other fringes. Intensity of dark fringe is 0. Here intensity of dark fringe is not 0. It is better to write it in a tabular form. All bright fringe have equal intensities. Here the central maxima, the central fringe has the maximum intensity, and the intensity will go down as you move further ahead. I'll give you a minute to note these points down. Then I keep on going again. The point that I'm showing you is not given in your sheet, it is given, it is double, but here is the value. All fringe width in the case of interference are of same width. Look at the screen, it is lambda d by d. Here all secondary fringes are of the same width, but the central maxima is of double width. All the secondary ones are having the same fringe width as beta, which is lambda d by d, but the central maxima is having double of the fringe width. Do we understand this? So note these points down. This point is not given in the sheet, so I am showing it from the second sheet. In case of interference, all interference fringes are of the same width. In case of diffraction, they are not of the same width. All secondary are of the same width, lambda d by d, but the central maxima is 2 times. I'll give you a minute to note this down.
Yes, sir.
Well then, just note down these 3 points. Again, these 3 points are in this sheet. The position of the maximas, nth maxima and nth minima, interference and diffraction, we are doing both of them together. For nth maxima in interference, we have n lambda d by d. For n at dark, 2n minus 1 d lambda by d. But here everything has been reversed. Position of n at secondary maxima, it is 2n plus 1. Remember, n starts from 1 here. 2n plus 1 lambda d by d. For n at dark minima, it is n lambda d by d. Path difference for maxima is n lambda. Here, path difference for maxima is 2n plus 1 lambda by 2. We have already discussed that. Path difference for minima is 2n minus 1 lambda by 2. Here, path difference for nth minima is n lambda. We have already discussed this. Yes or no? Please note down these points. And once we are done with these points, we will solve some question and answers. I will give you 2 minutes to note down these remaining points. Then let us move and solve some questions. This is question number 1. So very straightforward one. The bending of a beam of light around corners of an obstacle is known as what? A, B, C, D. 1, 2, 3, 4. What is the answer?
ये
Yes, beta, I can't hear you. What is the answer? The bending of light around the corners of an obstacle is known as, what is the answer? Answer is 3. It is known as diffraction. All of us know this. This is the simple definition of diffraction. Well done. Let us move to the next question. Question number 2. And the question number 2 is like this. The phenomena of diffraction can be observed when the obstacle is, and you have 4 options. Quite large, quite small, of the same order, bears no relation. Which one is the correct option here? A, B, C, D. 1, 2, 3, 4. Which one is the correct option? When is the phenomena of diffraction observed? What about the obstacle? What about the size of the obstacle?
C.
C is the option. It should be of the same order. Well done. This is a revision. As you can see, most of the questions are theory based. If you can understand these questions, if you can answer these questions, the concept becomes very clear. Comes question number 3 and 4. We have already discussed this. Who first observed the phenomena of diffraction? Question number 3. Question number 3. Who first observed the phenomena of diffraction? We have already seen the name. And the answer is 4. Grimaldi is the scientist who first observed the phenomena of diffraction. Yes or no? No or yes? Remember this, right? Question number 4. The occurrence of diffraction pattern depends on what? A, B, C, D. Width of the slit, wavelength of the slit, a wavelength of light, relative size of width and the wavelength, neither the width nor the wavelength. Which is the correct option? Tell me, bacha.
C, sir. C.
And the option is definitely C, sir. Yes, sir. The size of the width, the size of the width of the slit and the wavelength, they must be of the same order for diffraction to happen. Well done. This is the next question. Question number 6. We are trying to tackle all the sorts of questions that can come in this problem. And remember, most of the question will be simple. Phenomena of diffraction occurs. Number 1, A, B, C, D. all kinds of. Option A, light and sound. Option B, all kinds of waves. Option C, only electromagnetic waves. Option D, only light waves, but not X-rays. Which is the correct option here?
B, sir. B.
Yes, beta?
B. Bombay.
B, all kinds of waves. That is absolutely correct. That means this phenomena of diffraction, and you remember this diffraction, that is a good achievement. In one class, if we can remember so many stuff, remember, bacha, questions will be coming from this part only. Let me move to this question. Let us see if you can tell me the answer for this one. In Young's double slit experiment, diffraction is of which type? Fresnel, Fraunhofer, both Fresnel and Fraunhofer, neither Fresnel nor Fraunhofer. Which type of diffraction is happening? This is a question based on your understanding, and it's a question based on your knowledge. As simple as this.
B, sir.
B, it is Fraunhofer diffraction. Remember this, this is a question based on your knowledge, and you must know this. As you can see, the question will get repeated over and over. This is the next question, question number 11. And it again asks you the same thing, the correct relation between the size of the obstacle and the wavelength of light for Fraunhofer diffraction is what? Can I have your answers for this one? Question number 11 is what I am
Yes, sir.
talking about.
A. Assam.
A, it must be approximately equal to 1. Well done, everyone. Let us now move on to some more questions. And let us move on to questions that have previously come in the examination hall so that we have an idea of what type of questions are expected. And this is a previous year question from RPMT. Diffraction and interference of light refer to which phenomena? A, B, C, D.
B, sir.
B, wave nature of life. That is correct. Well done, bacha. Again, one more question. Again, we have discussed all these questions and the various types. And I hope that you can give me the answer for this one. The question comes on your screen right away. Sound wave shows more diffraction as compared to light waves. What is the reason? A, B, C, D. Question number 5.
A, sir.
A, wavelength. Well done. You see, that is great. I'm really impressed that you can recollect. You can recollect everything from what we have discussed. Again, I might put you on some sort of a numerical question, and this is a sort of numerical question that we can expect. The direction of the first secondary maxima in the Fraunhofer diffraction at a single slit is given by which formula? A sine theta is lambda by 2, A cos theta is 3 lambda by 2, A sine theta is lambda. We are talking about the first secondary maxima, bacha. Which is the correct option? Tell me. Remember, 2n plus 1 lambda by 2. You put the value of n as 1. So answer becomes A sine theta is 3 lambda by 2. Do we understand this? Yes or no?
Yes, sir.
That is the answer. And with this, we come to an end for this particular topic on diffraction. What we have done in today's class, we have understood what is the formula, what is the phenomenon of diffraction when light having the same wavelength as an obstacle, it encounters an obstacle, it bends. This phenomena is known as diffraction. In diffraction, we have superposition or superimposition of infinite number of coherent sources coming from a single wavefront. We have also seen the differences between interference and diffraction in tabular form in many forms. Remember, in YDSE, we are creating two coherent sources from a single source using this phenomena of diffraction. We have seen that the condition for maxima in diffraction is n lambda is equal to d sine theta. For maxima it is 2n plus 1 lambda by 2 is d sine theta. For minima it is n lambda. With this, I will wind up today's class. In tomorrow's class, in the next class, we will be dealing with the next topic, polarization. And I expect one question from diffraction and one question from polarization. And they are very simple, as you can see. Topic is pretty damn simple. So I'll see you tomorrow, same time. I hope you enjoyed the class. Take care and have a nice day, beta. God bless you all.